We are now recording. Let's get the slide from the current slide. Now, before we get started, a couple of issues. Nothing really important. The visual aid is here to let people know what's going to happen to students who don't get the test turned in on time. But that's beside the point. Okay, I'm just kidding. Okay. If you noticed, I have not worn glasses before. I have a long time ago, but not recently. And I had a cataract removed on Thursday. I wasn't on campus at all Thursday. And the new lens they put in, I can't read with it. Okay, they put it a little too far distance. They shot the difference between reading and computer screen, and that makes it so I can't read without reading glasses. So these are just reading glasses, but I can't see you with them on. I mean, I can see you, but you're really fuzzy. So I'm still getting used to the new system. So if I look really awkward doing it, that's why. I am pretty awkward. Okay. I don't know if these are not related, but just to let you know, they asked for what they call the no-show report to be done by today. I did it over the weekend, and that's where we report any student who is on the roll but has never attended class. Now we have 3, but they are not paid, so they weren't included in that. So I assume they're not ever going to be here. But all of you, there's no sweat for that because all of you have attended. In fact, everyone in the class that had paid has attended. But what I don't know, and this probably isn't related at all, but it could be that at some point they'll remove students who haven't paid from the roll. They're going to remove those who have paid but have never attended, but so far they haven't removed students who haven't paid yet. So I don't know, again, I don't recall if any of you have paid or not paid. My guess is all of you have paid. But if you know of any that have not, still working on the payment, whatever, be sure the business office knows what your plans are with that. So if they come to the point of removing unpaid students, removing unpaid students, they'll flag you so they won't remove you if they know you're in the progress of making payment. Okay. I was planning to get a lot done over my long weekend, but Thursday was completely out of the question. I basically slept all afternoon from the anesthesia that they gave for the operation, and I mean I was just worthless all day. And then Friday, I couldn't see enough to do anything. I couldn't read. I couldn't, and my eye was still dilated. So it was 2 days for it to go down, and so I had to wear shades just inside even, and I couldn't read to do computer work or to do anything else. So Saturday, when finally my eye was down, dilation had disappeared and stuff, finally we went to CVS and found some reading glasses that made it be able to see. So I got started I had a lot of things to take care of that I planned to do. I got some of them, and yesterday I got close to half of your papers graded. I don't have them in Blackboard yet, but they are graded. So the top half of the alphabet, pretty much those are graded. The scores are really good so far. And so if you do want to see what you made, I can show you that. I can't give it back to you because there's still a few papers out that have not been turned in. As soon as I get them all in, then you'll have your papers back. And they'll get on Blackboard at some point. Also, let me tell you about this week. It's going to be, I think, a really crazy week. What's not? I've been working on my instructor's evaluation. I'm the math department chair, and I've got all those completed except for a few people who hadn't turned me in some stuff. And I saw in my email this morning one person had sent that, so I'll get hers corrected. But for much of my office hours this week, I'm going to be trying to get signatures on evaluations. Now, some are on this campus, and that'll be no sweat. But others on the Birmingham campus, and there I'll have to go over there sometimes on Tuesday and Thursday and try to get evaluations signed there. Okay. All that said, Another thing that's coming up, tomorrow I do have my follow-up visit with the guy who did the cataract removal, but he's right across the road here. He's right over here. They did the operation at Eye Foundation Hospital downtown, and we live very close to that, so that was convenient. But my follow-up appointment, he's right across the road here on, at least on Tuesdays, and I think I saw him there one other time before we had the surgery. So he's right here. So the appointment's at 2:10, so I'll probably be off campus from about 1:45 until 2:30, 2:45, something like that. So I know I'll be off campus tomorrow for at least an hour in the afternoon, and I may be over on the Birmingham campus some, but I'm guessing that won't happen until Thursday. Okay. Is that enough announcements? Okay. And again, my eyes are sort of bizarre. Another thing, and let me go and get this said too, I'm having to put 3 different drops in them 4 times a day. And I did the morning drops this morning at home. The next shot I have is at the end of this class. But it's supposed to be 3 minutes between the drops because you don't want the different drops to interfere with each other. And I only have 5 minutes between classes, so that's not going to work too well. So if someone can be watching that, I hate to do it to you, but if you don't mind leaving maybe just a little early today, maybe 5 minutes rather than 11:25, 11:20, would that be okay with you? You wouldn't? Yeah, wow, y'all are so kind. So nice to give me that. I just can't believe it. Okay. All right. Any questions? Anything we've done so far? Okay, so someone keep up with the clock. I don't. Okay, and about 11:20, let me know. We'll have a break before then, but let me know. Any questions? All right. We're on example 8, page 137, section 2.4. Chapter 2 is differentiation. 2.4 is the chain rule, and we're what they call simplifying derivatives. Okay? And here is example 8. Again, things look weird. So, all right. Here's our problem. Okay? Well, here's another problem. Mine too. Okay. All right. Okay. What we're asked to do, they don't ask you, they just put it down there and it says simplify the derivative of a quotient. So, obviously, we need to take the derivative of that function. How would you go about doing it? You tell me. What's sort of wrong with that picture? Or not wrong, but inconvenient about that picture?
Fraction.
Is what?
Cube root.
Second?
The cube root in the denominator.
A cube root in the denominator. That's certainly an issue. Okay? How would you deal with that? Okay? Now, we can't change the problem. We can just change how it looks. So multiplying by something, that might be a little tricky unless you divide by the same thing, and then you're right back at the same problem. So what would you do? Any ideas? I think I've said before, there's 2 things I don't like when taking derivatives. I don't like radicals, and I don't like variables in the denominator. This has both. Is there any way we can rectify that situation?
We can change it from cube root of x squared plus 4 to x squared plus 4 times the 1/3.
To the one, and what?
That's an exponent.
Okay. All right. So that's one suggestion. I kind of like it if I could see it. Okay. I'm back and forth between glasses because I had eye surgery, and the new lens is fixed. I can't do any adjustment with the muscles like I used to automatically without thinking about it. But now to see up close, I have to have these on. All right. So you're saying, right, this is x over x squared plus 4 to the 1/3 power. Is that what I understood? Okay. Is that what you want to go with?
You can get out of the denominator.
How do you do that? Ha! I kind of like that idea too. X times x squared plus 4 to the minus 1/3. Both of those are perfectly doable forms. This form, you use the quotient rule. This form, you use the product rule. And have y'all gathered that I have a preference? Yeah, I like the product rule better. You certainly can do this with the quotient rule. My guess is that's how the book does it. But let's us do the product rule. Okay? Now that product of two functions, how does that work? Okay, let me see if I got you. It's when f of x is equal to g of, I can't write either, times h of x. Is that what you're saying? Then what would that be? The f prime would be what?
X.
Oh, okay, you're doing this problem. Okay, I thought you were saying g's and h's. My hearing's not good. Okay, yeah. So we'll start with that. We're going to start with with x. Goodness gracious. Let me erase that scribble if no one needs that as a reminder of product rule. Does anyone need that? Okay, so let's get rid of that. I thought that's what you were doing. Okay. All right. Okay, so we're doing the first times what? Second? The derivative of the second. Okay, and what is that?
2x.
Okay, there's going to be a 2x in it for sure. What else? Anybody? Anyone? Nobody? It's a power rule, right? Negative 1/3 times what? X squared plus 4 to the negative 4/3. Ding, ding, ding. Got it. Okay, so there's the first times the derivative of the second. What goes next? Okay, you need a sign there. Plus. Okay, good guess. Okay. Now, what goes next?
One.
Yes. Okay. I'll leave it. I'll write an invisible 1 there. Okay. Times what?
X squared plus 4.
That's it. X squared plus 4 to the minus 1/3. Okay. Now, product rule to me is a little simpler to do, but it has its cost. And here's where the costs come. You have different denominators. So let's fix as much as we can of this. Numerators, you have x times 2x. That's going to be a 2x squared. Okay? And we got a minus out front. Okay? In denominators, we got a 3. And we've got an x squared plus 4 to the 4/3 power. By that, have I accounted for everything? The minus sign, the 2x squared in the numerator, and the 3 and the x squared plus 4 to the 4/3 power in the denominator. Okay? Plus 1 over, there's my 1, okay, x squared plus 4 to the 1/3 power. By that. Okay. Now, that is an answer. It's not a simplified answer. Okay? So how can we simplify this?
We need to get a common denominator.
common denominator, because you got adding two fractional forms, need a common denominator. What's going to be the common denominator?
3x.
First going to be Jalen. Okay. I think I put you in the right place. Say again?
3 times
Yes.
x squared plus 4 to the 4th power.
Okay, that's going to be your common denominator. And how do you get this one? Already looks like that. Exactly there. How do you make this one look like that?
We need to multiply 3.
Multiply by 3. That means you multiply the numerator by 3 as well. Okay. How do you get this to look like that? Anybody? What's the difference? We got the 3's there. We got this part there. What's different?
4/3.
4/3 to get to 1/3. How can we make this to the 4/3 power? Multiply by something to the 3/3. This thing to the 3/3 power, right? When you multiply the same base, different exponents, keep the base, add the exponent, 3/4 plus 1, 3/3 plus 1/3 is 4/3. So you just multiply this thing right here, numerator and denominator. By that? Okay. So this up here is going to be an x squared plus 4 to the 3/3 power, which is to 1, and that makes this to the 4/3 power. Notice how I cheated and just wrote it in. Okay? Okay? Now we have common denominators. But our numerators are a little wacko, so let's work on the numerators a little bit. That's a very mathematical term, wacko. Okay. All right. I'm going to lead off with the first one because it's positive. I like positive better. So 3 times x squared is 3x squared plus 12. Let me go on and pull this one in there. Minus 2x squared plus 12. There's all my numerators combined over 3 times x squared plus 4 to the 4/3 power. Okay? Now, what you see you can do to simplify one more step.
Subtract 3x squared and 2x squared.
3x squared minus 2x squared is x squared plus 12 over 3 times x squared plus 4 to the 4/3 power. Now, if any of you want to go back and write this in the same form that your original problem was in, who would want to do that? But you could. You could just write the numerator as it is, 3 here in the denominator. I wouldn't mess with that. And then write this as this thing to the 4th power. And you can either put the 4th power in the parenthesis, in the thing, raise this to the 4th power, that would work, or do the whole denominator to the 4th power, that would work. Now, I don't know if the book goes to that extent to do that. I'm just perfectly happy leaving this in that form. There's no simplification by going back to radical notation. It's just that the original problem was in that, so you might need to. So for now, let's just say that's our best shot at the answer. Any questions? Okay. Let me clear my mess and see how they did it. Well, just like you said, Patrick said, let's just write that to the 1/3 power. Now, I bet you they're going to use the quotient rule. Yes, they are. Isn't this fun? How does the quotient rule go? You tell me. Say again? I don't know what your F and G are. This is F. That's where you're throwing me out before. Okay. How about this? This is real simple. Low D high minus high D low over low low. Remember that one? Low is the denominator. Okay. So the denominator times the derivative of the numerator, there it is. We saw that before. Minus this time, because this is quotient rule. High, there's the numerator, times the derivative of the denominator. Well, the derivative of the denominator is 1/3. This thing to the minus. Oh, did they ever make an error here, didn't they? That's supposed to be 4/3. Did they make the same error in the book?
Yeah, they did.
They did. This is unbelievable. Okay? That is supposed to be 4/3. Okay? In the book, that's supposed to be a 4/3. Unless I'm doing something seriously wrong, I don't believe I am, that should be a 4/3. Okay? So it's high minus high d low mod third times this thing to the minus 4/3 power times chain rule 2x. Now it doesn't matter. It's just like crazy and I can't rub it. Okay. Okay. That's that over the denominator squared. That should be the 2/3. They got that part right. Okay? This over that squared. So that is a 2/3. That one should have been a minus 4/3. Okay? Now at this point, we've got to fiddle with the numerator. Okay? And this is why I don't like the quotient rule, because now you have to mess with what's in that. So let's see how they do it so we won't reinvent the wheel. Oh boy. All right, they had a 1/3 here. They're going to pull it out of both terms, and okay. With their error in here, I'm not sure I can justify any of their mess here. Okay. All right. So they're going to pull the 1/3 out. Since this doesn't have a 1/3, it gets a 3. Okay. This was to the 1/3 here. They're also pulling this out of here. So that's supposed to be a minus 4/3. And if they did pull a minus 4/3 out here, then this would then be minus 4/3 plus 1/3. You know, when you do that, that would be to the 3/3. So this would be correct, okay? If that was a minus 4/3, okay? And then they have the minus 2x squared, which we had left over here, if that was a minus 4/3. So again, I'm pretty sure they have an error here, and I think they have the error here in the book. If I don't, if I've messed something here, then I'm writing my book in ink and I've really messed up. Okay, let me get Devin and Jasmine here. Did anyone else come in while I was running my mouth? Okay. All right. The book has, the slides and the book have an error in, as far as I can determine. But let's see. They pulled out the 1/3 and this thing here. So that's why they had to put a 3 in here. And when you're dividing out that, that's the same as this thing, and that leads us to the 3/3 power. So that part's right here, okay, I think. Minus 2x squared is all they got here. And then this is correct. This is over to the 2/3 power here. So that's okay. Now, it's going to be interesting to see what they do next. Okay. They got the same answer. Just not certain of their technique, okay? These two go together to make this, so that makes it look like they're okay here. I just can't rationalize that, because when you take the derivative of that, that's why I do not like the quotient rule. There are some errors in here, and I can't figure out how they mask them over to come out with the right answer. But we got the right answer with the product rule, much easier than this. So we'll just let that go. What's that?
How'd you get a 12?
I'm sorry?
How'd you get a 12?
How to get the 12?
Yeah, I'm trying to
Okay. If you'll notice here, 3 times x squared is 3x squared, plus 12 minus 2x squared. So 3x squared minus 2x squared is x squared plus 12 from there. Okay. That 3 is right, and this, it would look like what they did was right with the 2/3 there, but that step right there bugs the fool out of me here, because it's supposed to be derivative of the denominator, which would be 1/3, which is correct. Derivative of this would be, oh, sorry, that is right. Sorry, I did make a mistake there, because they left it in the numerator. Okay, so theirs are correct, okay? Okay, because, I messed up in my book, okay? Okay, because the derivative of the denominator, this denominator, subtract 3/3 from 1/3 and you get minus 2/3. So that is correct. It wasn't a minus 2/3 or minus 1/3 because they had it in the denominator as a positive 1/3. So sure enough, that's right. Then they pull that out and everything else flows from there. Okay? When they pull out a minus 2/3 from that, that's minus a minus, which makes a 3/3 here. So that is perfectly correct. They did do it right, and I messed up in my book. Okay. Yeah. And this won't erase because I did it in ink. Okay. So I'm going to go back and write minus 2/3 and minus 2/3. So yeah, they did do it right. Sorry about that. But I still think that's more complicated than the product rule. But pay your money and take your choice. Hopefully all of you have paid your money, so you take your choice. Quotient rule, product rule, you get the same answer. Okay? Ooh, they're even doing example 9. Good for them. Now, the one difference here is, example 9, you can go to larsoncalculus.com for an interactive version of this type of an example. Oh, boy, look at this one. Y is equal to 3x minus 1 over x squared plus 3 squared. How would you proceed with that? There's a multitude of ways to do this. Which way would you like to do? They're all correct. Some of them may be a little easier or harder than the others, but they're all doable. How would you do it? What would be your first step? And it's not the Texas 2-step. This is going to be far more than 2 steps. How would you go? You tell me. Make a guess.
The square.
Say again?
No, it's square.
Okay, deal with the square? Is that what I heard? I heard it somewhere, I don't know. So let's do this. Y, well, my pen is not working well. There we go. Y prime is equal to 2 times this mess, 3x minus 1 over x squared plus 3 to the first power. Right? Power rule. But then you have chain rule times the derivative of what's inside. So start with the power rule. 2 times this thing, raised to the 2 minus 1 is to the first power. That's the easy part. Now you do derivative of that. Okay? So I'm going to write it this way, times 3x minus 1 over x squared plus 3 prime. Now we're just taking the derivative of that. This is a really weird way to do it, but since y'all started me off, deal with the square, I said, okay, let's do that. How do we take the derivative of that thing? Two obvious choices, one really obvious, the other one maybe not quite so obvious. Second, quotient rule, is that what I heard? Certainly doable, okay? So this will be 2 times 3, that's an ugly 3, x minus 1 over x squared plus 3. And then how does the quotient rule go? You don't want to do my little song, huh? I don't sing well anyway. How do you do it? It's not that funny. Okay, never mind. Huh? No, you start low. Start low and go high. Okay, no. All right. Low D high. So that's x squared plus 3. This is why I don't like it. I don't like to sing well. Times D high. What's the derivative of the numerator? Easy question. 3. Okay. What follows that? Minus. Now go high. 3x minus 1. I can't write. That's a 3x minus 1. It sure doesn't look like it, does it? Three x minus 1. What's next? 2x. 2x, D low. Okay. Over what? X squared plus 3 squared. Low, low. Okay. All right. This takes a little bit of work here. Big surprise. You have a 2 out here, a 3x minus 1 over x squared plus 3. Leave that alone for now. Let's deal with that numerator. Let's first distribute. And what does that give you? Anything? 3x squared plus 9 minus 6x squared. Say again? Plus 2x. Okay. Over x squared plus 3 squared. Leave that alone for now. Okay. Now we can still do some work with that numerator. So we'll leave the 2 alone for here. We'll leave the 3x minus 1 alone for now. The x squared plus 3 alone for now. And what can we do with that remaining numerator?
Subtract the 6, so it's negative 3x squared plus 2x plus 9.
Okay, what did you wind up getting?
Negative 3x squared.
Negative 3x squared
Plus 2x.
Plus 2x
Plus 9.
Plus 9 over x squared plus 3 squared. Okay? Now, you might, if you wanted to, try factoring the numerator, okay, of this thing. I personally don't think it's going to get you very far.
You have to take out the 3.
Say again?
You have to take out 3 first.
Take out a 3, you said? Okay, well, that's a 2 there. That's not a 12. That's a 2.
No, no.
I know. You're making fun of my writing. Okay, I understand, but it doesn't hurt. Not much, okay? I don't think that will factor in. Even if it did, you're not going to be able to eliminate anything from the denominator anyway, because that's a term like that. So, and I see no reason to multiply them together. So frankly, the only thing I would do with that was combine the denominator and make it 2 times 3x minus 1 times, and frankly, I don't like starting with a minus sign, so I'm going to do 9 plus 2x minus 3x squared, even though that's not in whatever you call it, descending order of the powers. But you can multiply those together and make it x squared plus 3 cubed. Okay? Now, that's a messy looking answer, but anything else you're going to do is going to get it just as messy. I don't see any way to simplify any of that. Okay? Now, maybe the book will prove me wrong, but let's see. Any questions on that? I would say, did you want to try doing that second term, this thing right here, with the product rule? That would be 3x minus 1 times x squared plus 3 to the minus 1, and do the product rule with it. You'll get the same answer, but it's, I think, a little easier, but it's still not very easy.
How would it look?
Huh?
How would it look?
How would it look like this? The 2 times 3x minus 1 over x squared plus 3 times, and this is what you're taking derivative of, 3x minus 1 times x squared plus 3 to the minus 1 power. Okay. And that's what you're taking the derivative of. Okay, and then you would do, and it doesn't really matter which goes first here, this times derivative of that, which will have a minus 1 in it, and this thing becomes a minus 2, and then plus this thing times 3. And to me, that's going to be easier to work with than this, but they're still messy. They're still going to be messy at the end. You can't eliminate that. So let's see how the book did it. I bet you they did quotient rule, and let's see if they simplified it any further. Okay? So first they did 2 times this thing to the 1 power. That's what we did. And whereas I put it as a prime, they put d by dx of this, which is fine. Same thing. Okay? So their first step, just like ours, general product rule, power rule, I'm sorry. And then they fiddled just a little bit here, but basically they're going to leave this alone, just multiply it by 2. And then they did quotient rule, low d high minus high d low over low low, just like we did. And that became this. I think that's exactly what we had, 2 times 3x minus 1. Okay. Now they went on and combined the denominators at this point. We hadn't at this point, but it's okay. But they got the 3x squared plus 9 minus 6x squared plus 2x. And then they did their last step, which is 2 times 3x minus 1 times negative, they left it in descending order of power, negative 3x squared plus 2x plus 9 over that. And they left it there. Just like I said, no reason to try to simplify or multiply or anything else. I don't think anything's going to work. So there's your answer. Same as we got. Any questions? Okay. Now, that was example 9 on page 137. Oh, we move right to trigonometric functions and the chain rule. Okay? The chain rule versions of derivatives of 6 trigonometric properties are, okay, what is derivative of sine u? Say again? Okay. Cosine u, the only only difference is, since u may be a derivative of x, you put a u prime after. What's the derivative of cosine? Negative sign, and then you do just a u prime after that. Because this is not the same as that, you assume there could be. What's the derivative of tangent? Secant squared times u prime. How about this? Cotangent? Only minus cosecant squared u du. Okay? This one? I'll be reading my hand. Okay? Anyone remember? Oh, come on. I hear mumbling. I can't make it out. Yeah, and then the only thing is you do a u prime, and this one would then be negative cosecant u, cotangent u, du. Okay, u prime. All right, and when they write them like this, notice these functions here are the functions without the cos in front, sine, tangent, and secant, and the derivatives are all positive. Those with the cos in front, cosine, cotangent, and cosecant, they all derivatives are negative. That just happens to be, there's nothing magical about it, it's how helps me remember it, okay? If you don't, it doesn't helpful to you, don't bother with it, okay? But those are your chain rule versions. If this was x, you just leave this part off, okay? But if that's u, then you have a u prime. You take derivative of the outer function, then derivative of the inner function. Okay? So, let's do example 10. What would be y prime there? Help me somebody. A little louder. Cosine 2x? Times 2. Got it. Okay? Because the derivative of the inner part is just 2. So it's 2 cosine 2x. Very good. Does that make sense, or any questions? Got it? Yeah, question? No.
I thought it would be, 2 sine. Cosine 2x times 2 sine.
Times 2 what?
Sine. I thought it would be
No, okay, yeah. You don't mess with that. Take the derivative of the outer function first. That's derivative of sine is cosine. Same function here, 2x. Then take the derivative of the inner function. That's what they're doing here, and that's just 2. Well, they put it here. I don't like putting it here because then you may think that's multiplied there. No, put it in front, and now it's clear it multiplies the whole thing. Okay? Make sense? Okay? I bet you this would be. What do you think this will be? Negative sine of x minus 1, and then the derivative of that is just 1, so it's negative sine of x minus 1. Because the derivative of this thing is 1. That's all. So it doesn't change anything. Does that make sense? Minus sign is there because the derivative of cosine is minus sign. Okay? And derivative of this, though, is just 1. Okay. Now, if you wanted to go back to your sum and difference of sign formulas, you could do more with that. Well, I don't want to do that. I hope you don't either. Okay. How about this one? What would that be? Secant squared of 3x. Say again?
times 3.
Times 3. Perfect. So it's 3 times secant squared 3x. I'm used to doing the times 3 at the end, but please always put it back at the beginning, because if you just look, well, with parentheses in there, it's pretty clear. But if you had just put a dot or something in between there, you would think, well, is that 3x times 3? No, it isn't. This is times the whole thing. So I like to write it like that, and so does the book. Good for them. We agree on something. Okay? All right, so here's the summary. Wait, that can't be all, can it? No, it isn't. That was example 10. We still got 11, 12, and 13 before we hit our summary. All right, so let's do example 11. Parentheses and trigonometric functions. Okay. I think it's what we were just doing, but let's just do these. Y is equal to the cosine of 3x squared. Okay? Now, do any of you for a moment think that the square might be on the cosine? Pretty obviously it's not. Okay? Neither is it 3x squared. You'd have to have parentheses there. So the only thing they're saying here is if it's a cosine squared, you put the square right by the cosine. With the square over here, it's just a 3x squared. So what would be the derivative of that? Say again?
Negative sign.
I can't hear. Negative sign? Okay. My hearing's bad. Negative sign of what?
6x.
Of what?
6x.
Don't do them both at once. 2 steps. Texas 2-step. 3x squared is the derivative of the outer function at the same thing of the inner, is your f prime of g of x. The g of x doesn't get changed until the next step, and it is, now you do 6x. 6s. Okay, no, okay. Now I'd bring that out front and write it as minus 6x sine of 3x squared. And if you want to, put parentheses around the 3x squared, just like you could have in front of the cosine of 3x squared there. Put parentheses around that. If it helps you see, do it. Now these are the cases where a lot of people do this automatically for all of them. They do the derivative of the inside first and then the derivative of the outer function. And this really does well here, except then the minus sign gets messed up. But yeah, there's always something. But your answer is minus 6x 3x, of sine of 3x squared. Okay? The B one here is y is equal to cosine 3. This is a strange problem. I've never seen a problem like that I had to take a derivative of. But it's a very legitimate problem. What does that mean, by the way? Cosine 3 is just a constant. 3 is measured in what units?
Degrees.
No. If it's degrees, you have to have a degree sign. If you don't see a degree sign, you understand it has to be radians. Okay? So this is just a number. Cosine 3 is just a constant, like 17/3 or something like that. It's not 17/3, but it's just a number. So basically, this is just a power formula for x, a constant times x squared. So what would be the derivative of that?
Negative sign.
No, don't mess with negatives. This is just the power function of x. The exponent times the coefficient to this will reduce by 1. That's all, folks. That's just a coefficient. That's just a constant. Cosine 3 is just a number. So that would be 2 times cosine 3. Remember your power rule, your exponent times your coefficient times x. Now you could put the parentheses just around the cosine 3. It doesn't matter where you put them, but that's what you've got. It's still just a constant times x. That's all. That's all it is. Don't mess with taking the derivative of this, because the derivative of a constant is 0. Exactly. That's just a constant. Okay? So, okay. They wrote it differently, and it almost threw me. They wrote it as 2x times the cosine of 3, which is another perfectly fine way of writing it, Why, I do not know, but they wrote it that way. Perfectly fine. Now, if you're doing WebAssign, they would count this one wrong. They say wrong answer and looking for that one. I probably wouldn't come up with that in a few thousand years, but maybe not a million years, but a few thousand to figure out that's what they were trying to get to. Don't know why. Okay, let's do the C one. Y is equal to cosine of 3x squared. What would you do in a problem like that? Taking a derivative. Y prime. And there's several ways you can approach it. I don't care. How would you approach it? You don't have to jump right to y prime if you want to do something else first. Hint, hint. What would you do? I've got the hiccup, sorry. Anybody? Just tell me. What would be your first step? If it's wrong, I'll just laugh at it. I mean, no, I'll just say, no, try this. Okay, no.
The derivative of the cosine is negative sine.
Okay, so you're going to start with that, okay? So you'll be a negative sine of?
9x squared.
Aha, 9x squared. Okay, perfectly good. That was correct. Times what?
Derivative of 9x squared, which is 18x.
18x. Okay, and when you combine all that together, that'd be minus 18x sine of, you could write 9x squared or go back and write that. Either, it doesn't, to me it makes more sense 9x squared. Frankly, if I were you, if I were doing this, I would have started with this. I would square that one. Say this is the same as cosine of 9x squared. And then done the derivative of that would be minus sine. Yeah, I would have gotten the same answer, but just done it that way. Okay? Let's see what they got. Negative 18x sine 9x squared. Perfect. Okay? D. Y is equal to cosine squared x. What would be your approach to that problem? What would be your y prime? You tell me. What would be your first step? I don't always do this, and maybe I should, especially since we're fairly new on chain rule. Maybe say, what's the inner and the outer function here? Would that be helpful to think in those terms? Give me a guess. Anybody? Second? You certainly are going to need to find the derivative of cosine, and what is that? Minus sine x, except, yeah, minus sine x. So that's going to be in the mix somewhere.
Do you, like, do something like this?
Times 2, is that what you're saying?
Yeah.
Cosine x. Yeah. Perfect. Now combining things together, taking the minus and the 2 together, minus 2 sine x cosine x. Okay? Now, that was perfectly correct. The way you did it was fine. I tend to, because I'm sort of anal retentive, go 2 times cosine x, that's the outer function, times the derivative of cosine x is minus sine x, you get the same result. Right? See what I'm saying? The outer function here to me is the squaring function. So do a power function for cosine, 2 times cosine to the first power, then times the derivative of cosine, which is minus sine, which is exactly what you did or you did it in reverse order. It's perfectly fine either way. Good answers. They put cosine first, it doesn't matter. And again, if you're doing WebAssign and you didn't have it in the order they wanted it, they tell you it's wrong when it's not wrong. So I'm not a real big fan. Never mind. Y is equal to the square root of cosine x. What would be your first step if you're taking a derivative? Yes, I do not like to try to take the derivative of a square root, so I write this as cosine x. Okay, and you can write it either of two ways. The way I understood you to say of cosine x to the 1/2 power, that's fine. Or you could have written as cosine 1/2 x. Both of those, they mean the same thing. And then what do? That just rewrites it for you. What's your y prime then? Do not leave off the parentheses here, because then it looks like cosine of x to the 1/2, which is a totally different problem. So if you're going to write it in with 1/2, be sure you put parentheses there, or if you write it like that, it's obvious it's cosine being square root, not the x. But whatever. What would be your next step? Say again? Okay, there's certainly going to be a negative sine x involved. That's the derivative of the inner part. Okay, times a 1/2. Is that what I heard? Cosine x to the negative 1/2. You subtract 1 from that, right? Power rule. Okay? Now again, I probably would have done it in the, once you are written like this or this, 1/2 cosine x to the minus 1/2. I would have written minus 1/2 here. It doesn't matter. 10 times the derivative of the inside, which is minus sine x. Okay? Now, this one doesn't clean up nicely, but it does clean up some. Your numerator, you got a minus out front. Numerator is sine x. Denominator has a 2 in it. And if you wanted to go back and put your square root, it would be the square root of cosine x. Okay? Or if you didn't want to go back to that, you could have just left it as negative sine x over 2 cosine x to the 1/2. Or cosine of 1/2 x, you know, any way you want to. That would be, they wrote it in this form. And there's no clear pattern of what they like, whether they don't like the radicals or do like the radicals. It's just they write them sort of randomly, but that's the form they left it in. Both of those are fine, perfectly fine. This is a correct answer, but it's just a little messy, okay? So it's usually better to get numerator denominators sort of separated, okay? Whether you go back to radical form or power form, I don't care. I prefer power myself, but since the original problem was the radicals, I don't mind going back to that. All right, any questions on those? All right. Yes?
For the very first one, why is it 6x?
This one?
Yes.
And what was the question?
Why is it 6x?
Oh, because the derivative of the inner part is 2 times 3 times x to the 1, 6x. See?
And you got 9x squared for the third one?
Okay, that one because the 3x was in parentheses squared. So square that, I like to square that first, make it 9x squared, then you do the same thing, and that's going, the inner part of that is going to be 18x. Okay? Because of those parentheses, those sneaky little parentheses, they're designed to trip you up, right? No, minus signs are that, whatever. All right, ready for 12? Any other questions? Great questions, by the way. 12? Okay. F of t is equal to sine cubed of 4t. Okay? Now, what have we got going on here? This is a composite function with three pieces. You got the cubic function, to me, is the outermost function. The sine function is the next outermost function, or the next innermost function. And then 4t is the final innermost function. So what in the world do you do with this? Okay, say that one more time. F prime of t, is that what you're doing, or are you doing something else here? Oh, you want a parentheses here like this, sine of 4t cubed, like that? Yes, that's okay. If that helps you see it, by all means do it. And then what you do with that? That's a second? Yeah? What's that? Okay, and how would you do that? Okay. The way you've written it, it's just like a power rule, right? So it's the exponent times coefficient, coefficient's 1, so that'd be 3 times the function, sine of 4t, but reduce that by 1, and that would be square. Okay? Now you do the derivative of the inner part. That's the outer part. What's the derivative of the inner part? Well, that's a composite function. What would be the derivative of that? Cosine of 4t times what? 4. Perfect. Derivative of the inner part, okay? Derivative of 4t is 4. Okay, so now we combine the things together that we've got here, and 4 times 3 would be 12. Sine squared, I like the squared there, but you don't have to, of 4t times the cosine of 4t. Okay? Nothing much you can do to simplify that. If you don't like the center dots, put them in parentheses, however you want to do that. But that's your answer. Okay? And if you wanted to leave the sine of 4t with the square on the outside, that's fine too. Don't put it there, put it there. It's perfectly fine either place. Does that make sense? Question? Uncertain? You keep doing the chain rule of the, find the outermost function. This is how I do it anyway. Find the outermost function, do it. Derivative of that, of whatever that innermost was. Then do the derivative of the next outermost function of whatever its innermost part is. Then do the derivative of the next innermost function. This time, that's it. Derivative of 4t would be t. Would be 4. Make sense? Okay. Let's see. Oh, here, how did they write their answer? Okay, without parentheses, they did 12, sine squared 4t, cosine 4t, which is fine. To me, the parentheses help separate a little bit more, but it's perfectly fine the way they did. They didn't even put the center dot. Okay. Ready for 13? Yay or nay? Any question on this before I erase it? All right. 13. Ooh, going back to our favorite old tangent lines, right? Find an equation of a tangent line. What we're looking for is an equation of a tangent line. Okay, equation of a tangent line to the graph of f of x is equal to 2 sine x plus cosine 2x, Okay? At the point pi 1. Okay? Now, we'll hold off before I write the rest of it because I am a cynic. I'll admit that from the very beginning. I want to make sure this point is on this curve. Okay? The graph of that curve. So if I plug in for the x, the pi, what's sine of pi? Anybody? Sine of pi. Second? 0. So this one goes to 0. What's 2 times pi? Easy question. 2 pi. What's cosine of 2 pi? 1. So 0 plus 1 is 1. Yes. So that point is on the curve. Yes, yes, yes. All right. So we're going the equation of a tangent line of that function. Now the next part of it says, then determine all the values of x on the interval 0 to 2 pi at which f of x has a horizontal tangent. Okay? So we'll come back and do that in a minute. So let's do the equation of the tangent line of this one. What are we going to need to know the equation of any line? 2 pieces of information to get an equation of a line. What do we need? A point. Do we have a point? What's your point? Yeah, pi 1. That's your point. It's on the line. I just showed that. Okay? What else do we need? We either need another point, which we don't have, and I guess we could make one up, or what else would work? To have an equation of a line. A line meaning a linear equation. Line, linear. You got it? What else do we need? A slope. How in the world are we going to find a slope? What's the Jesus answer? Have I told you all that before? Does that make no sense at all? Okay, sorry. I don't know if any of you, I know a few of you do, but if you go to church or anything, a lot of churches nowadays, they have what they call children's church. And they'll have all the kids come up front. This is somewhere after they're done singing and stuff like this, and they want to get rid of the kids. I mean, they send the kids to other things so they can have the regular sermon. So they have children's church, and they bring them all up in front, and they have them sit there, and then usually some honcho, like the pastor or some other leader, will get up there and try to be real cozy with the kids and ask them some question. Usually they ask some question to begin with. It's just a good way icebreaker. Of course, the kids are sitting here. You know, they're scared to death. They don't know what to do. They're in front of the whole congregation, and they don't say anything. Finally, some little boy in the back will usually say, Jesus, okay, because he figures that's going to be a good answer in any church, right? Okay, ask a question. Jesus, they never tell you that's the wrong answer, do they? Okay, so that's why I say in Cal 1, when there's a question, the Jesus answer is take a derivative, right? Usually what we do in Cal 1, right? Not going to be far from the right answer here. So guess what we'll do? To find the slope? Take a derivative. All right, so let's do f prime. What would that be? Help me, somebody. Second? 2 cosine x. Good first start. Plus, or maybe not. I'll leave the sign off for now and let you tell me what it will be. Second? Minus sine 2x. Chain rule. 2. Okay. That's why I left a blank there. Does everybody see that? Yay or nay? All right. So there's the first derivative of that function. Okay? Where do we want to know the first derivative of the function? At pi 1, exactly. So let's do f prime at what value for x? Pi, okay? And what would that be? Okay, but what's cosine of pi? Ooh. Cosine of pi.
It's 1.
Almost.
1/2.
Huh?
Is it 1/2?
Cosine starts at 1, and then at pi halves it goes down to 0, and at pi it goes down to -1. Okay? So this will be a -2, right? And what's 2 times pi? That's a hard one. 2 pi. And what sine of 2 pi? No, we're doing this one. Sine of 2 pi. 0! So this is -2. The slope at that point is -2. So we have a point and the slope. What's the equation for the tangent line?
Y minus y1.
What's your y1?
-2.
At
Oh,
1 is equal to, now, -2 times x minus pi. Strange looking equation. Yeah, it's a strange equation, but it's okay. Equations can be strange. This would be y minus 1 is equal to minus 2x, you finish it, plus 2 pi, and now we add 1 to both sides. And you get y is equal to minus 2x plus 2 pi plus 1. It's a strange thing. This is your slope, and there's your y-intercept. Okay, 2 pi plus 1. That's whatever that is. Okay, 6.28 plus 1 would be about 7.28 or so, somewhere in there. Okay, so there is your equation of the tangent line. Done. Okay, now let's just stop and make sure they got it right. They have minus 2x, and they put the plus 1 in front, plus 1 plus 2 pi. Fine. They don't put parentheses around it. Fine. It doesn't matter. Okay? We got the same answer they did. Now, that's the first part of the problem. The second part says, then determine all values for x in the interval from 0 to 2 pi, and that's an open interval, at which the graph of x has a horizontal tangent. Okay. What's going to be true about a function having a horizontal tangent? Anybody? Make a guess. Okay. That's if we were finding one-to-one functions, and we're not really interested in that here, but that is a good connection, but just not the one we're looking for here. What's true about a horizontal tangent line? Any horizontal tangent line. What's true about all horizontal lines? Second? Slope is 0, exactly. And we've got right up here what the slope is. What is the slope of a line? Of a function of a line? It's the first derivative. So we set that first derivative equal to 0 and find all the values of x which make that equation true. Okay? What's the first thing you're going to do? Any ideas? Not very imaginative today, are we? Here you have an equation. We want to solve that equation. What's the first thing we could do? Just to make it look simpler. Okay, what if that was 2w plus or minus 2v is equal to 0? What would be the first thing you would do? (2w minus 2v is equal to 0. Instead of w, cosine x, I put a w. Instead of sine 2x, I put a v. If you're trying to solve that equation, what would be the first thing you do? I would do anyway, because I like it to look as simple as possible. Divide out the 2's. 2 will go into 2 once, 2 will go into 2 once, 2 will go into 0. 0 times. Okay? That was easy, right? So what does that leave it? We'll just get rid of the 2's. Okay? Gone. So now we have cosine x minus sine 2x is equal to 0. Now, let me write it down. Cosine x minus sine of 2x is equal to 0. Now, what's wrong with that picture? What's awkward? Messy? Two different arguments for your trig functions. So, do you know anything about the function sine of 2x? Does that have a simplification? As in a double angle formula, you trig students? I would hide my head too if I couldn't remember that, huh? What's the double angle formula? Sine 2x. Anyone? Okay. Not all of you have books, I don't think. Let's see if, oh yeah. If you do have a book, like at the inside front page, it's one that you could tear out if you wanted to. It has many of these trigonometry identities. And there's one that says double angle formulas. Sine of 2u is what? 2 sine u, sine x, cosine x. I went back to x's. So let's rewrite that. Cosine x minus, instead of sine 2x, we'll put 2 sine x cosine x equals 0. Okay? Now what would you do?
Factor out cosine.
Ah, fantastic. Factor out a cosine x. Cosine x, what's left in the first term? 1 minus 2 sine x is equal to 0. Now what do you do with those? Set each of those separately equal to 0. So either cosine x is equal to 0 or 1 minus 2 sine x is equal to 0. Okay? We can do something about figuring out what values x's make this true between 0 and 2 pi. Where is cosine x equals 0? What values for x? Cosine x equals 0 between 0 and 2 pi. Second? Cosine, no. Sines are 0 at the whole pies. Cosines are 0 at the half pies. So what half pies are between 0 and 2 pi? Pi halves and? Second? One more. 3 halves pi. So that would be our two values here, pi halves or 3 pi halves. They're in between 0 and 2 pi. Okay, let's get to this one. What would you do to the second equation there?
Do you move the 1 and divide by 2 first?
Okay, I would move the 2 sine x and say 2 sine x is equal to 1. Is that okay? I'm just lazy that way. And then do what? Divide by 2. And that gives me sine x is equal to 1/2. Now, what values of x between 0 and 2 pi would sine be 1/2? Oh, wait, we already finished it. We passed that course. We don't need that anymore. Do we? No, we do. Of course we do. What? Values of x between 0 and 2 pi will give you sine x of 1/2. Pi 6. So this will be x equal pi 6. Any others? Okay, let's draw a picture of what sine x looks like between 0 and 2 pi. Okay, so there's going to be pi, there's going to be pi halves, here will be 3 halves pi. Okay, now sine starts here, goes up to 1, so there's that first 1/2 right there at pi 6. It goes down to 0, goes down to -1, and back up to 2 pi. No. Oh, yeah, there is, isn't there? Another place where it's 1/2. Sine is positive in the first and the second quadrants, and it has to be between 0 and 1, so somewhere in the second quadrant, it's also 1/2. What value would that be? Another thing about sine, even though my picture doesn't look like, this is a nice symmetrical curve here, right? So if the first 1/2 is pi 6 from here, the second one is going to be pi 6 from there. What's pi 6 from pi?
Is it 5 pi?
5 pi over 6. Perfect. So here's the other one. 5 pi 6. Okay? We have 4 values for which you would have horizontal tangents between 0 and 2 pi. The first one would be at pi 6, then at pi halves, then at pi 6 pi, and then at 3 halves pi. Okay? Now, they drew the figure in the book. I don't want to draw it, so I'm going to show it to you on the board here. Poor people at home won't be able to see it because they can't see my book here. But here is a graph of that function. And there's at pi 6 a horizontal tangent, at pi halves a horizontal tangent, at 5 pi 6 a horizontal tangent, and at 3 halves pi another horizontal tangent. Then the rest are outside 0 and 2 pi. Does that make sense? Okay, I can't hold this up forever. So hopefully you got it. Any questions? All right. Let's finish this section and take a quick break, okay? Because I see some people look like they need one, and I know I need one. So let's just finish this last slide. Here are a summary of your differentiation rules so far. General differentiation rule, let C be any real number n be a rational number, not integer, but rational number, u and v be differentiable functions of x, f be a differentiable function of u. Okay, not v, but u. Okay? The constant rule, derivative of a constant is what? 0. Okay? Simple power rule. Derivative of x to the n would be? Help me.
1.
At n. X to the nth. N, x to the n minus 1. Perfect. Okay? And then this one, d by dx of x is 1. Okay. d by dx of cu. I see you. No, never mind. What would that be? C times u prime. You pull the c out and then that. Okay? How about the sum or the difference? D by dx of u plus or minus v. U prime plus or minus v prime. Perfect. Okay? Product rule. Oh boy, our favorite. What's that?
N times prime of v plus prime of n plus times v.
Okay, u v prime plus v u prime. Perfect. Quotient rule. Oh yeah, we love this one. What's that? Oh, second?
U prime times v.
No, okay. Start low.
U prime times v.
Okay. vu prime
Minus UV prime.
minus uv prime over vv. Okay, v squared. How about chain rule? d by dx of f of u. Help me, somebody.
We're doing the chain rule.
Yeah, chain rule.
F prime.
F prime of u times
U prime.
u prime. Perfect. Okay. General power rule. Now this one was with x. Simple power rule. This is with u. It's just a chain rule of the general, basically. What's that?
N times the u.
To the n minus 1 times,
Oh, times u prime.
yeah, the u prime. You got it. Derivative of sine, cosine, derivative of cosine, negative sine, derivative of tangent, derivative of cotangent. Oh, you said secant squared. Derivative of cotangent, negative cosecant squared. Derivative of secant, secant tangent, derivative of cosecant, cosecant cotangent. Negative. Remember, the cos have negatives. Okay, now the things they didn't do on here, if these had not been x's but had been u's, they'd have been followed by u prime. Okay. Got it. Any questions on those? I think that's the end of this section. Homework exercises in this section will include any of the odds 3 through 7. They're all at Calc Chat. 3's at Calc View. Any of the odds 9 through 33, a whole passel of them, maybe a passel and a half. Okay? They're all at Calc Chat. 9's at Calc View. Any of the odds 35 to 53, they're all at Calc Chat. 37's at Calc View. Any of the odds 55 to 59, they're all at Calc Chat. 61's at Calc Chat. Any of the odds 63 through 69, they're all at Calc Chat. Any of the odds 71 to 77, they're all at Calc Chat. 75's at Calc View. 79's at Calc Chat. 81's at Calc Chat. That's one like we just did. Any of the odds 83 to 87, they're all at Calc Chat. 89 or 91, they're both at Calc Chat. You can look into doing either 93 or 95. They should both be at Calc Chat. You can think about doing 97 if you wish. It's at CalcChat. 99 should be at CalcChat. 101, I would say any of the odds 101 through 105. They should all be at CalcChat. Then any of the odds 107 through 113, they should all be at CalcChat. Then using absolute values, we haven't done many of those. I think we did something somewhere in the past. Either 115 or 117, they should both be at CalcChat. 119 should be at CalcChat. Then there's a couple of true false, 121 and 123. They should both be at CalcChat. All right, we will end there for now, and we'll pick up with, I don't know why I have to go back here. We'll pick up at 2.5. All right, but let's take a quick break. Let's try to keep it 5 minutes or less. And I will pause the recorder. All right, start from the current slide. And chapter 2 is still differentiation, a pretty long chapter. 2.5 is implicit differentiation. Everything we've been doing up till now has been what we call explicit differentiation. You're given a function, f, in terms of the independent variable x, and you differentiate, okay? So what we're going to do, our objectives here, is first distinguish between functions written in implicit form and explicit form. And we'll use implicit differentiation to find the derivative of a function, okay? Sounds pretty simple, but what do we mean by implicit and explicit functions? Most functions have been expressed in explicit form. Y is equal to 3x squared minus 5. Here's your dependent variable y by itself, all alone, naked out there by itself, and here on this side is everything in terms of x. No y's over there, and x's are all differentiable. The variable y is explicitly written as a function of x, how we're used to writing functions. Some functions, however, are only implied by an equation. For example, the function y is equal to 1 over x is defined implicitly by, if you multiply both sides of the equation by x, you would have xy is equal to 1. Okay? Well, you say, but isn't this explicit? Well, it is. This, though, is written in an implicit form. Now, written explicitly, you can see there is a problem there. What is it? One over x. What can x never be? 0. You can never divide by 0. You can never take square roots of negative numbers. You can never take the log of a negative number or 0, either one. So here you see that x can't equal 0. When you write it in this form, and think about it just a little bit, then you see that not only can x not be 0, but y can't be 0 either. And if you think about this, yeah, y can't be 0 here either, because 1 over anything is never 0. The only way you could get y to be 0 is if it be 0 over something. Well, that doesn't have it. That's 1 over x. So this is written in implicit form. In other words, the x's and y's are tied together. Here, that's written explicitly. Y is a function of x. Okay? Excuse me. Okay. Now, to find dy dx for the second equation, you can write y explicitly as a function of x, like here. And then I don't like taking the derivative there, so write it in exponential form, x to the minus 1. Then I can take a derivative. What's the derivative of x to the minus 1? A little louder? good. Negative x to the minus 2, which if you then wanted to write back as another form, that would be negative 1 over x squared. Okay? Now, this one, even though they gave it to us implicitly, you could rewrite it explicitly and go from there. Okay? So that strategy works whenever you can solve a function explicitly. This is implicit, but you can solve for y by dividing by x and go for it. You cannot, however, use that procedure when you're unable to solve for y as a function of x, such as here. X squared minus 2y cubed plus 4y is equal to 2. Can you solve that as a function of y alone? Good luck. You can isolate the y's. 2y squared plus 4y is equal to x minus 2 minus x squared. Yeah, but you can't isolate the y. Because this one has y cubed, that has y. There's no way you can isolate the y. For that equation, it is difficult to express y as a function of x explicitly. So to find dy dx, we use what we call implicit differentiation. Okay? Implicit differentiation. Take it at face value here, exactly what they give you, and start taking a derivative with respect to x. What's the root of x squared? Say again? Let me get my pen. Wait. Okay. What's the root of x squared? 2x. This is as a function of x. Okay. Minus. What's the root of 2y cubed as a function of x? First part should be pretty similar. Say again? Say again?
2y squared.
Okay, it's that 3 times 2. 6y squared, but you got the chain rule here. Because y is a function of x, then you do the chain rule, y prime. Right? So you didn't need to do that with x because the root of x with respect to x is 1. Okay? But with y, you have to use the chain rule. Okay? Plus, what would that next term be? Second? 4 what? Y prime, exactly. Okay? And then what's the root of 2? 0. Good deal. Okay? What we're looking for is dy dx, which is the same as y prime. So now we isolate the y primes. Okay? Let's move those to one side. And that will be, the 2x does not have a y prime. So that would be 2x is equal to 6y squared y prime plus 4y prime. Oh, minus 4y prime. Y'all almost let me get away with that, didn't you? What were you saying?
One of those have to be a minus.
I can't hear.
One of those have to be a negative.
Yeah, oh yeah, okay, and you're absolutely right. You subtract, you add that to both sides, subtract that from both sides, okay? Now, guess what we do next? What we're looking for is dy dx or y prime, so factor it out. Right? It's a factor of both sides. We put all the y primes over there, all the terms without y primes over here. So then this would be 2x is equal to 6y squared minus 4 times y prime. Right? Or you could factor it the other way. That's fine. Now we're trying to isolate the y prime, so we'll divide both sides by 6y squared minus 4. 6y squared minus 4. And that's what your answer is. dy dx, or y prime, is equal to 2x over 6y squared minus 4. You can't write it as an explicit function of x, but you can write it implicitly. So here's your y prime. That's what it is. It's got a y in it, but there's no helping it. No way to isolate or separate that, but you've done it. That's what we call implicit differentiation. Make sense? Just remember, chain rule. Anytime you take a derivative of the y, go on and take it, but then you have to have a y prime with it. When you take derivatives of x, just take the derivative of x and you're done. If you're taking the derivative of the constant, that's always 0. Okay? So, I jumped ahead. I probably shouldn't have, but y'all were so eager to have it, I just couldn't help myself. To understand how to find dy dx implicitly, you must realize that the differentiation is taking place with respect to x. That's what I kept saying. That means that when you differentiate terms involving x alone, just differentiate as usual. However, when you differentiate terms involving y, you must apply the chain rule, and after you do the things with the y, then you always have a y prime, because you're assuming that y is defined implicitly as a differentiable function of x. That's your assumption. Stick with it. Okay. This is awfully easy. What is that? Anybody?
3x squared.
3x squared. Perfect. Okay? The variable here, you're taking the derivative with respect to x, so just take it. Okay? It's done. Okay? How about this one? Okay, I heard a 3y squared. That's certainly the first part of it, but what else? Y prime, because you have to then take the derivative of the inside function, which is your y, with respect to x, dy dx. The variables here are not the same, so you have to do the chain rule part at the end. You start out the same, but then you have to do the chain rule. Here, no chain rule involved. Does that make sense? Okay. How about this? d by dx of x plus 3y.
Be 1 plus
1 plus
3 times the y prime.
3y prime. You got it. Okay? Or write it dy dx if you want to. All right. Does that make sense? Implicit differentiation. Implicit differentiation. Just regular old differentiation. All right. Oh, there's a d. What will that be? Oh, boy. What are we going to do with that? Anybody? Say again?
Product rule.
A product rule. And how does that go?
HD over DX.
Get a little louder. X times, is that what you said?
Yeah, X times
X times
D over DX. Y squared.
Okay, wait. Okay. If you're doing product rule, the first times derivative of the second would be x times 2y dy. Okay. Okay, here it is. Oh, okay. They're taking extra steps. Plus y squared. Perfect. And that's it. So they're taking an extra step here, and that would be x times 2y dy plus y squared. Perfect. And carrying that one more, that would be 2xy dy dx plus y squared. Okay? That's about as simple as you can get that one to go. Okay. Any questions? Okay, I think that's the last one. Yes. Okay, that was example 1. Now let's look at implicit differentiation, as if we haven't already been doing that. The guidelines for implicit differentiation differentiate both sides of the equation with respect to x. Okay? Collect all the terms that have a dy dx in it on one side or the other. They say on the left-hand side, and move all the other terms that don't have a dy dx in it. They may have y's in it, but if they don't have a dy dx, move that to the right side. It doesn't matter which side. Move all to one side, ones with dy's on one side, ones without dy's to the other. Then, on that side where you have all your dy's, every term has a dy in it, factor out the dy dx and whatever is left over, and then solve for that dy dx by dividing by whatever was left over, like we just did. Okay? Now, this is not the same one we did, but I think we can do it. So, how would you proceed here? Find dy dx for that function, which I can't solve explicitly, so we have to do it explicitly. Implicitly, how do you do it? Lead off. Somebody. Three y squared, y prime, I like doing it that way, plus 2y, second, y prime, minus 5, y prime, minus 2x equal 0. Good deal, folks. Now what? Second? Okay, yeah, you ultimately, but let's get all the y prime terms together and the ones without y prime on the other side. So that just means 3y squared y prime. I'm all with you. Let's just go on and factor it at the same time, okay? Factor out the y prime. I think you're almost as lazy as I am, aren't you? Okay. Y prime, and that leaves a 3y squared plus 2y minus 5, and move to the other side, the 2x. Okay. Devin wanted to skip a step, right? Okay, so we did. Now we did two things there at once. We moved the 2x to the other side, making equal 2x over here, and then all these terms in it, those three all had y prime in it. Factor out the y prime, that leaves you 3x squared from this one, a 2y from that one, and just a minus 5 from that. Now what? Last step. And they call it dy dx, so I'm going to go back and call it that. Dy dx is then equal to what? What you do? What's that last step? We're wanting to isolate the y prime. So what do we do? Second? Did you say divide? Yeah, divide both sides by this thing right here. 3y squared plus 2y minus 5. 3y squared plus 2y minus 5. And these go out, and that leaves your dy dx is equal to 2x over 3y squared plus 2y minus 5. Done. Can't separate it any further, can't solve for y or anything else. All you're looking for is dy dx. There you've done it. You've isolated it, separated everything else on the other side. Make sense? All right, good deal. Let's see how they did. 2x over 3y squared plus 2y minus 5. Good deal. Any questions? Now, let me also point this out to you. We haven't had, when you can solve a function explicitly for y, if it's a function, then someone mentioned earlier the vertical line, horizontal line test. When you solve for a function for explicitly, you can always pass the vertical line test. Can't always do horizontal, but boy, when you have these implicit functions, they can look like this. That doesn't look at all like a function because it fails the vertical line test in many places. Well, it's still an expression, and you're differentiate the expression, and that gives you all sorts of weird values in there, but sure enough, you can still differentiate. I can't hold it up any longer. This derivative, you see, there will be at least two values. Well, no. There could be multiple things that will give you the same number, when these combinations come into play. So you're no longer dealing with just pretty functions, one-to-one functions anymore. Okay. Let's see. Oh, let's see how they did it, by the way. I just did it my way. Let's see how they did it. Probably pretty similar. Differentiate both sides of the expression with respect to x, okay? And they wrote in a lot of extra terms here that we didn't. But if this helps you see it, by all means do it, okay? So d by dx of y cubed would be 3y squared. Well, okay, they're going to write it each term. All right, they're going to do the gory detail here, okay? Taking derivative with respect to every term on both sides, okay? Then the first one's going to give you 3y squared, chain rule dy dx, 2y dy dx, minus 5 dy dx, minus 2x equal 4. There's you taking the derivative of both sides of the equation term by term. Okay? Now you might notice all three of these first three terms have dy dx's in them. The last one doesn't. Move it to the other side. Okay? I keep thinking someone's standing here. It's not. Okay? And that gives you 3y squared dy dx. Okay? Plus 2y dy dx minus 5 dy dx is equal to 2x. Move that to that side. That's all your y prime terms on this side. All the terms of that y prime on the other side. Okay? Then factor out the dy dx. And that's what we've done here. That left us the 3y squared plus 2y minus 5 equal to 2x. And now isolate the dy dx, dividing everything else, and that gives you dy dx is equal to 2x over 3y squared plus 2y minus 5. Any questions? Went back and did the same thing we did. Took a lot more time and effort, but they showed every step. Any questions? That was example 2. Oh, here's that picture. I didn't have to hold up the book. To see how you could use an implicit differentiation, consider the graph shown here. There's that exact function we just did. Okay? Believe it or not, only it's not a function, not in the xy sense. Okay? From the graph, you can see y is not a function of x. Even so, the derivative can be found and is found, just like we did. Is a formula for the slope of the tangent line at a point on the graph. Any point on the graph you can find. You have to be on the graph. The slopes at several different points are shown below the graph. At 2, 0, that's a negative slope, negative 4/5. Okay? I wish they showed the derivative on it. Oh, here it is. Okay? Because when you, okay, first thing, make sure 2, 0 is on the graph. Okay? If you put a 0 in for y, that would be a 0, that would be a 0, that would be a 0, and this will give you a minus 2 squared, which would be minus 4, that's equal to minus 4. Yes, that point is on the graph. Okay? The slope there, plugging 2, 0 here into this, that would be 2 times 2 is 4 over, put a 0 here, that would be a minus 5, that would be minus 4/5. There's the slope. Now, they claim the point 1, negative 3 is on the graph. Let's see if it is. When x is 1, y they say is negative 3, that would be negative 27 plus 9 plus 15. 9 and 15 is 24, so that's a minus 3. Minus 1 would be minus 4. Yes, that point's on the graph. 1, negative 3 is on the graph. Then let's plug that value into your derivative. And that would be a 2 in the numerator, and this would be 27 minus 6 would be 21, minus 5 is 16, 2 over 16 is 1 over 8. All right, so that was all that. Point on the graph. Say x equals 0. That's a strange point. When x is equal to 0, you have y cubed plus y squared minus 5y is equal to minus 4. That's sort of dumb. Okay. But they should have a y value here, they don't. And the reason they don't, it's a weird value, okay? It's not negative 3, it's something a little beyond negative 3. Negative 3 point something though. So they just leave x equals 0 here, and that would just be y cubed plus y squared minus 5y is equal to minus 4. Whatever y value gives that to you, that is, to find out what it is. Okay? Plug that in here though, x equals 0 here, it doesn't matter what that denominator is, the numerator is 0. So you do have a horizontal slope there. Now, at the point 1, 1, y is equal to 1, that's 1 plus 1 is 2, minus 5 is minus 3, minus 1 would be minus 4, so yeah, 1, 1 is on the graph, but it's slope of the tangent line, when you put a 1 in here, you get a 2, you get a 1 here, you get 3, plus 2 is 5, minus 5 is 0, undefined slope. Vertical slope there at 1, 1. 1, 1's on the graph, but not there. Negative 1, 1 appears to be the same thing. So there's, at least those 2 points have undefined slope. They're on the graph, no problem there, but their slopes are vertical lines, so they don't work. So this one we said looks like it's negative 5/4. Right here, just barely positive 1/8 here, 0, and there. Okay, that was so much fun. Okay. Any questions on that? It was just a lot of blah, blah, blah. Okay. So it's meaningless to solve for dy dx in an equation that has no solution points. Okay? X squared plus y squared equal negative 4. Why do an implicit differentiation? Because you know that has no points. Because x squared plus y squared can never equal negative 4. Okay? So don't even try that. Make sure your equation makes sense. However, if a segment of the graph can be represented by a differentiable function, dy dx, then dy dx will have a meaning of the slope at each point on the segment. Recall that a function is not differentiable at points with vertical tangents and at points where the function is not continuous. Okay? 2 things to watch out for. All right. Now, they skipped from example 2 to example 5. So let us do 3 and 4 first, and then we'll do 5. Okay? Any questions so far? If possible, represent y as a differentiable function of x. Okay? The A part here is x squared plus y squared is equal to 0. If possible, represent y as a differentiable function of x. What you think? What's your first thought when you see that?
Can you find the derivative of 0?
You find the derivative and set it equals 0. Is that what you're saying? Okay. You could do that, but let's step back a step or two first. What does that describe? X squared plus y squared equals 0.
Tangent.
What?
Tangent.
Okay.
Circle.
It's okay. A circle of radius what?
1
Really?
thing.
This equals 0.
Oh, it's 0.
Okay. A circle of radius 0. Can someone draw me a circle of radius 0? It is a point. Okay. 0, 0 is the only point that makes that equation true. So why would you want to take a derivative of a point? You can't, okay? So don't even bother with that one, okay? It says, if possible, represent y as a differentiable function of x. You can't do it. If you tried to, this would be y squared is equal to minus x squared. And what's wrong with that picture? That would be your first step, wouldn't it? What's wrong with that picture? This side is always positive. This side is always negative. Is that ever going to work? No. You can't have a positive number equal to a negative number unless both of them are 0. And that's all you got. You only got when x and y are both 0. So that doesn't really make any sense. Okay? So, how about this one? X squared plus y squared is equal to 1. Okay? It says, if possible, represent y as a differentiable function of x. What you think?
This one's wrong with the circle.
This will be a circle of radius 1. Okay? So let me just attempt to draw a circle of radius 1. Ugly circle, but don't make fun of it. Okay, this is 1, 0. This is 0, 1. This is minus 1, 0. And 0, minus 1. Okay? Now, it says, if possible, represent y as a differentiable function of x. What you think?
You can subtract both sides by x squared.
Okay, so we'll do that, minus x squared on both sides. So now we have y squared is equal to 1 minus x squared. Okay, and then what?
Do the square root.
Take a square root of both sides. Y is equal to the square root of 1 minus x squared. One little thing missing. Take the square root of both sides of an equation. What do you have to include? Plus or minus, exactly. Now, what we have here are two functions. One is the positive square root of x, that's that one, and the other, give me a different color.
Green.
Second, green? Second?
Green.
Green. Okay, I can't hear well. Here is the minus square root of x. Okay? Now, that's not a function, that's two functions. And there's something else, a little bit of a problem too. They said differentiable functions are both of those differentiable functions. At everywhere except the endpoints. Because there, both of them have vertical tangents, don't they? So, you can do, I don't know. Okay. I'll do the second one. Y is equal to minus the square root of 1 minus x squared. And that's only defined for minus 1 less than x less than 1. Not less than or equal to. The endpoints are not included. And the other one would be, the top half of the circle would be this one. Y is equal to positive the square root of 1 minus x squared. And again, minus 1 less than x less than 1. Can't include either endpoint on either one of them, but that's the best you can do. Two different functions, we can call it, say, y1 and y2. Two different functions. Okay, y1 and y2. But they're limited on their representation. All right, how about, let me go to a clean page. Everybody got this so far? Okay. X plus y squared is equal to 1. Get back to the dark color. X plus y squared is equal to 1. What would this give us? What would you do that? Again, it said, if possible, represent y as a differentiable function of x. What would you do? Subtract x from both sides, and that gives you y squared is equal to 1 minus x. Then what? Take a square root of both sides. Y is equal to what? Anybody? Okay, I'll write down 1 minus x, square root of 1 minus x. What am I missing? Plus or minus again. Okay, so it's not one function, it's two functions. Okay? Now, any problems with those functions? Here you have a radical, right? What's inside the radical? What's true about it? Has to be only take the square root of positive numbers. So 1 minus x has to be greater than or equal to 0, which means you can do it either one of two ways. I like to do it 1 is greater than or equal to x. In other words, x is less than or equal to 1. Okay? So basically what we've got here is that's x equal 1. You got a parabola this way, green again, or a parabola this way. Okay? Now my parabolas aren't very pretty, are they? Don't answer that. Okay. More like that. Okay. Now, we still got yet another problem. Anyone think of what that is? Similar to before. You cannot include the vertex of that sideways parabola. Now, my parabola stinks. Okay, I admit that. You know, the points here should be, I think, 0, 1 and 0, minus 1. I think those are both on those. Yeah, because x, when x equal, no. Yeah, when x equals 0, y is equal to either plus 1 for the top one or minus 1 for the bottom. Right. Okay. So, mine don't look symmetric, but just imagine they were. Okay? So, what does it say here? If possible, represent y as a differentiable function of x. Again, you can't take the derivative here because it's a vertical tangent. So that's why we have to exclude the endpoint. So this would be y is equal to square root of 1 minus x for all x is less than or equal to, well, less than 1. We can't include the equal sign because of the vertical tangent line. It is a point on the graph, but it's not differentiable there. Or go back to the green, y2 equal minus 1 minus x. Again, for x less than 1. Okay. I guess the other thing would call this a y1. Okay. That's about all we can do there. Does that make sense? Okay. Now, example 4. They don't have in the slide set, so let's us do it to it. And this one you can see larsoncalculus.com for an interactive version of this type of example. Determine the slope of the tangent line to the graph of x squared plus 4y squared is equal to 4. Okay, we want the slope of the tangent line. Okay, at the point radical 2 comma negative 1 over radical 2. Okay. All right. Again, cynic that I am, I want to make sure that point is on that curve. Okay? Your x value is root 2. When you square root 2, what do you have? Not that hard a question. Square root 2, what do you have? 2. Okay? Now, when you square minus 1 over root 2, that's your y value, what does that give? Say again? You square minus 1 over root 2. See, that's the y value. Square that and what do you get? Square negative 1 over root 2. 1/2, and multiply that by 4 and you get 2. So here you had a 2 plus 2 equal 4. Yes, that point there is on that line. Okay, we got it. Okay? So we want the slope of the tangent line at that point. How are we going to get the slope of the tangent line? That should be an easy question. The Jesus answer. Take a derivative. So let's do it. Say again? Okay.
No, I'm confused. What is
In Cal 1, when there's a question, usually a pretty safe answer is take a derivative, okay? It may not always work, but it's going to work a lot, okay? So that's why I said that. Sorry about that. I don't mean to offend anybody. If it's offensive, I won't say it anymore, okay? Now, take a derivative. I thought someone was doing that, and I wrote down the first part.
You'll get 2x
2x plus
8y
8y
times dy
y prime, or dy dx, is equal to 0. Okay? And what else can you tell me from there?
Subtract both sides of 2x.
Subtract 2x from both sides, and that gives you
8y y prime equals
okay,
and then divide by 8y.
by 8y. So that gives you Y prime is equal to
Negative x over
4y. Okay? Now, you've taken a derivative. What do you do next? What do you do with Glade? Plug it in, of course. So you plug in that point for these values. And what does that give you? The slope of the tangent line at that point would be a minus, and your x is root 2, and your y is, you got 4 times negative 1 over root 2, right? Now, I'm going to simplify that a little bit. That would be a minus root 2 over a minus 4 over root 2. Well, one thing, minus and minus are going to become a plus, and then this would be root 2 times root 2 over 4, right? When you divide by a fractional form, multiply by the reciprocal, right? And this gives you root 2 times root 2 is 2 over 4 is 1/2. So the slope of the tangent line at that point should be positive 1/2. And that's what the book got to. Okay, now they're not going to show this on the slides. So this one I'll try to hold up here as long as I can hold it. That is an ellipse, by the way. I don't know if you recognize that in an elliptic form, but it is. There's a point 2, negative 1 over root 2, and the slope there does look like it's about 1/2. Okay? So, yep, that seems reasonable, if not heavy. Okay. Any questions on that? All right. They have a little remark at the bottom, which is a pretty pertinent one. To see the benefit of implicit differentiation, try doing example 4 with the explicit function y is equal to negative 1/2 the square root of 4 minus x squared. Take the derivative of that one and see if you don't prefer implicit differentiation a little bit better. I think you will. All right, any questions on that? If not, let's erase that if there are no questions. We lost several people breaking. I hope that doesn't mean that we shouldn't have breaks to keep from losing people, but I know Loud is missing. Was there anybody else? See, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 4, 6, 8. We lost 2, Lyle and 1 others. Yeah, patience. Okay. All right, now we're ready for example 5. Example 5. Determine the slope of a graph of 3 times x squared plus y squared squared is equal to 100xy at the point 3, 1. Any of you guess what I want to do first? Verify this point is indeed on that graph. So for your x's, we're going to put in a 3, and for y's, we're going to put in a 1. So this is going to be 3 times, what's 3 squared?
3.
Yeah, for x. So that's what? 9 plus 1 squared? 1. 9 plus 1 is? 10 squared is? Times 3 is? 300. And this is 100 times 3 times 1? 300. Yes, it works. Okay? So that point is indeed on that graph. Okay? Everybody see it? All right. Now, it says determine the slope of the graph of that thing at the point 3, 0. We know the point, 3, 1. 3, 1 is on the graph, so we can determine its slope. How do we do that? Take a derivative, good deal, okay? So let's take a derivative of the left-hand side. What do you notice about the left-hand side? Anybody?
The squared outside.
Okay, it's a power function to begin with of another function. So let's first do the square. What does that give us? 2 times 3 is? 6. Okay. Okay. Times x squared plus y squared. Right? Okay. The outermost function is a squaring function. You do it of the thing on the inside times what then? Links in a chain rule. Okay. All right. What would be the derivative of the inside? 2x plus what? 2y. You missing something? Y prime. Okay, we've taken derivative of the left-hand side completely now, is equal to 100 is the easy part. I'll pull that on the outside. Now, xy is a product. So what would be the product rule? No, that's quotient. I don't see any highs and lows in a product here. We got problems here, Houston. Okay? And you said it backwards anyway. So never mind. Okay. Derivative of xy. It's a product.
X times y prime.
xy prime. Well, wait. Yeah, xy prime plus
Prime YX? No. Prime XY.
okay, how do you write prime xy?
This is just 1.
X is, okay, so derivative of x is 1 times y. Is that what you meant?
That's good.
All right, good deal. All right, now this is admittedly a little messy, okay? Now, the algebra, the calculus is not bad. We've already done most of the calculus. The rest of it's just math, okay? It's messy math, I agree, but it's just math. So let's just take, this is a number, 6x squared plus y squared. Multiply it by 2x. That would be 12x times x squared plus y squared. Okay? That's this thing by the 2x, right? Plus this thing by the 2y prime. So that would be 12y x squared plus y squared y prime. Agreed? I have a feeling I've lost people pretty badly and sadly. Okay? All right. Now we got 100 times these two things. The first one is 100 xy prime plus 100y. That one was easier, right? Okay. Now the reason I did it that way, rather than multiplying all these things out and that out and stuff, is I just want to isolate the y prime terms and the non-y prime terms. So I want to pull this one over here and that one over there. Okay? So I'm going to have the 12y times x squared plus y squared y prime minus 100 xy prime. Those are all the y prime terms on one side, equal to 100y minus 12x times x squared plus y squared. There's all my non-y prime terms on the right-hand side. Okay? Factor out the y prime. What do you have left here? 12y times x squared plus y squared minus 100x is equal to all this mess. 100y minus 12x times x squared plus y squared. All right, and then let's divide both sides by this. 12y times x squared plus y squared minus 100x. Okay. All right. There's my y prime. That mess here. Okay? But what were we interested in? Determine the slope of the graph, there's the y prime, at the point. So guess what we do? Plug in 3, 1 into that mess. Okay? And again, so this y prime is equal to, and this is at the point 3, 1. Okay? Plug it in, plug it in. The y is 1, so this will be 100 minus 12 times 3 is 36 times, let's just do this once. We know what that is. 9 plus 1 is 10. Okay? Divided by 12 times y is 12 times 10 minus 300. Okay? Let's see what we can figure out of that. The y prime at 3, 1 is going to be 100 minus 360 over 120 minus 300. Okay? That's going to be a minus 260 over a minus, I believe that's 180, isn't it? Okay, I'll cancel out some zeros there and come up with 13 over 9. I sure hope that's the answer. Oh, look at that. It is. 13 ninths. I know they're ugly and messy, but you know, how do you eat a 5,000-pound elephant? One bite at a time. Just take one step at a time and go through and follow through with it. Don't do any unnecessary combining if you can help it. Leave things however they are. At the end, when we plug in the numbers, they'll be much easier to do than otherwise. Okay? Now, what's that? Stop right here. Well, I'm going to let you see how they did it, which won't take long. But that's exactly what I was thinking too. You take the derivative of both sides, and derivative of this side with respect to x is equal to the derivative of that side with respect to x. Okay, let's do this side. And what do we have? 3 times 2, coefficient times exponent, times this thing to the first power, times the derivative of the inside, which is 2x plus 2y dy, dx. On this side, the 100 comes out, and then your product rule is x times the derivative of y plus y times the derivative of x. Okay? Now, we want to get the y's together, So this one over here, which is 3 times 2 times 2, that'll be your 12y times this thing times that thing, minus 100 times the x dy dx over here is equal to, and there's 100y on this side, minus 12 times x this time times that expression there. Okay? Just like we did, factor out the dy, and you have 12y times x squared minus y squared minus 100x is equal to all that stuff on that, so dy dx equal to that. Divide by that denominator, that coefficient here. Now, why did they do that? I don't know. They put the minus 100 in front and the plus 12 there. I guess to make it look more like that. It doesn't matter. And then what you do now is just plug in. There's really no use in simplifying. It doesn't hurt. Yeah, they factored a 4 out of the numerator and a 4 out of the denominator, and they left with that. Yeah, that will make the calculations a little bit easier, but there's no real, what that is, that point, at that point, the slope of the graph is shown here, and that's what they call a lemniscate, okay? Skate, okay, lemniscate, okay? It's a thing that looks like the 3 ones on the curve. Slope there was, they don't even show the slope yet, but it's 13/9. Goodness, I think mine was easier than this, 13/9, which is greater than 1, but less than 2. Okay? Yep, that looks about right. Okay, obviously, there's some places the slope is not defined, okay? Here, here, and there, okay? And everywhere else it is defined, but you have to have a point on the. Okay, that was example 5, and that is the last example, hold on, that they show on the power. So we'll go to 12.6 next time. Let me erase this. Let me give you a few homework exercises here. I don't want you to have absolutely nothing to do. Let me find my marker page. Homework exercises here. Do any of the odds 5 through 19. They're all at Calc Chat. 5's at Calc View. 21 and 23, they're both at Calc Chat. 23's at Calc View. 25 to 31, they're all at Calc Chat. 25's at Calc View. Try doing 33 and or 35. They're both at Calc Chat. 33's at Calc View. 37 or 39, they're both at Calc Chat. 39's at Calc View. 41, another lemniscate. It's at Calc Chat. 45's on ellipse. Or 43, you can look at doing that if you'd like. 45's on ellipse. They both should be at Calc Chat. I think we'll hold off there and pick up the rest of those next time. Good deal. All right. We'll see you on Wednesday.